All right, let's shift focus to linear programming and how it fits inside Gurobi. Now, linear programming forms the base layer of mathematical optimization. The structure stays simple: linear objectives, linear constraints, and continuous decision variables. That simplicity gives it tremendous reach because many large planning and allocation problems reduce cleanly into this form. Gurobi's LP solvers are built to handle very large instances, including cases with millions of variables and constraints, while keeping solve times practical. And to reason about any linear program, it helps to separate structure from solution. The structure describes what decisions exist, what relationships restrict them, and what outcome the model tries to optimize. Once that structure exists, algorithms take over and search for an optimal corner of the feasible region. Okay, and problem structure here. At the structural level, decision variables represent quantities under control, usually modeled as continuous values. The objective function assigns as a linear score to every possible decision vector. Constraints restrict feasible choices using linear equalities or inequalities, and a variable bounds further limit ranges and often encode physical or operational limits. And together, these elements define a polyhedral feasible region where optimization occurs. Okay, now solution methods here. Solving that structure requires algorithms designed for linear geometry. Primal simplex walks from corner to corner of the feasible region while improving the objective. A dual simplex operates from the dual side and exists during reoptimization and sensitivity analysis. Barrier methods, also called interior point methods, move through the interior of the feasible region and scale well for large sparse models. And a Gurobi can run several of these approaches concurrently and select the fastest outcome automatically. So when you see the standard formulation here, uh, that looks like this. And conceptually, the objective measures weighted usage of decisions. The constraints measure feasibility and the solver searches for the lowest achievable value within those limits. And Python time. Here we have a basic LP example for production planning. Let's begin. The import establishes access to the modeling interface and solver constants. The model class acts as the container for everything that follows. Okay, so here the model object gets created and named. This step initializes internal data structures that will later hold variables, constraints, and objectives. So the data section encodes the problem context, products from index set, profit values, define contribution per unit, labor and material coefficients describe resource usage. Available labor and material define goal limits and global limits, and this separation between data and model logic makes the formulation readable and easy to extend. So, decision variables are added next. Each variable represents how much of a product to produce. A lower bound of zero enforces non-negativity, and the continuous type reflects fractional production being allowed. So, here the objective aggregates profit contributions across products. The quick sum expression builds linear objective efficiently. Maximization tells the solver to search for the highest total profit consistent with constraints. Okay, and here labor constraints block. This constraint limits total labor usage. Each product's labor requirement gets multiplied by its production level and the sum stays within available labor. Conceptually, this enforces a shared resource cap. Okay, let's continue. And the material constraint works the same way, limiting total consumption across all products. Multiple constraints like this carry out the feasible region. And calling optimize hands the full model to the solver. Parasol simplifies the formulation. Then the LP algorithms compute an optimal solution. And after optimization, the solver status indicates whether an optimal solution was found and variable values can be extracted for reporting. Okay. Now we have a table. So, different LP algorithms serve different structures. Primal simplex works well when good starting bases exist. Dual simplex excels for re-optimization and sensitivity tasks. Barrier methods handle large sparse systems efficiently. And concurrent models run several strategies in parallel with deterministic variants available when reproducibility matters. Okay, another Python example is here, this time transportation problem. Okay, now here, imports Gurobi Py, and look at that. Supply values define how much each factory can ship. Demand values define how much each warehouse requires. Transportation costs assign a per unit cost for every factory to warehouse pair. And this setup models a flow problem over a bipartite network. Okay, so let's continue. A model part, a new model gets created to represent the transportation system. And variables. Now, each variable represents a shipment quantity along a route from a factory to a warehouse. The args list defines all possible routes, and lower bounds enforce non-negative shipments. Okay, and the objective minimizes total transportation cost. Each shipment variable contributes cost proportional to its route. Okay, and supply constraints ensure total shipments leaving a factory stay within its capacity. These constraints balance outgoing flow. So demand constraints here, demand constraints ensure each warehouse receives enough total shipments to meet its requirements, and these constraints balance incoming flow. And final part, once optimized, the model yields a minimum cost shipment plan. The objective value reports total cost, and positive shipment variables describe the routing plan. So, okay, what is next? Sensitivity analysis. Now, once an optimal solution exists, the next question usually sounds like this. How stable is that solution when inputs change? Sensitivity analysis answers that by explaining how the objective and decisions respond to small parameter shifts. This layer turns optimization results into decision support rather than a single static answer. Okay, now after solving a linear program, the solver already holds all the information needed for sensitivity analysis. The key point here is timing. The sensitivity attributes become meaningful only after an optimal basis exists, which explains why optimization appears first in the workflow. Okay, now this call finalizes the solution and fixes the basis used by the LP algorithm. From this point onward, dual values, reduce cost, and allowable ranges reflect that optimal structure. Okay. And some checking parts here. Checking the solver status ensures the solution reached optimality. Sensitivity values rely on that condition because they describe behavior around the optimal basis. That's okay. And these loop walks through each decision variable and reports several attributes. The variable value shows the chosen level in the optimal solution. The reduced cost indicates how the objective coefficient will need to shift before that variable changes its role in the solution. The reduced cost of zero signals active participation in the basis, and the objective coefficient range shows how far the coefficient can move while keeping the same structural solution. That's okay. And conceptually, reduced cost measures resistance. For a variable sitting at zero, it tells how much incentive must increase before that variable becomes attractive. For a variable already active, the reduced cost stays at zero, reflecting balance at the margin. And the second loop switches focus to constraints. Each constraint carries a dual value, often called a shallow price. And these numbers measures how the optimal objective reacts to a one-unit change in the constraint right-hand side. Slack reports unused capacity. The right-hand side range shows how much the limit can move before the optimal basis changes. So here, the shadow price captures marginal value. A positive dual value means relaxing the constraint improves the objective. A zero value indicates extra capacity carries no immediate benefit at the optimum. So that's okay. I'm looking. Can I say yes? Now, allowable ranges describe local stability. Within these ranges, the solver keeps the same structural solution while objective values or limits shift smoothly. Outside these ranges, a different basis becomes optimal and sensitivity numbers require recomputation. So here, putting these pieces together gives practical insights, and the reduced cost explain which inactive decisions remain unattractive. Shadow prices reveal which resources carry economic value at the margin. Allowable ranges define safe adjustment intervals where conclusions remain valid.